Right now, as you watch this video, your head is aging faster than your feet. Not by much, imperceptible, tiny, but real. Happening now. Every second, your head, your feet, different clocks. You think time is absolute, universal, the same everywhere. One cosmic clock ticking the same seconds for everyone. Wrong. Fundamentally wrong. And I can prove it with a clock and a ladder. Every single second, the clock on your nightstand runs slower than a clock on your ceiling. The difference is tiny, about 90 nanoseconds per day per meter of height. But it's real, measurable, proven thousands of times. This isn't poetry, this isn't metaphor. This is gravitational time dilation. And it's one of the most disturbing truths about reality. You've heard that time is relative, that it speeds up or slows down depending on how fast you're moving. That's special relativity, weird enough. But this is stranger. Time doesn't just flow differently when you're moving. It flows differently when you're standing completely still. Just because you're at a different height. Your brain is experiencing more time than your liver. Right now, your eyes aging faster than your toes. The GPS satellite passing overhead is experiencing time 45 microseconds faster than you are every single day. And if engineers didn't account for this, your GPS would be off by miles, within hours, useless. How is this possible? How can time itself, this thing that seems so absolute, so fundamental, be running at different speeds in different places? The answer begins with a rocket ship, an elevator, and the most powerful idea Einstein ever had. But first, you need to understand what we even mean when we say time flows differently. No absolute clock exists. Nowhere in the universe. Time is what clocks measure, nothing more. And identical clocks built the exact same way, with the exact same mechanisms, tick at different rates, depending on where they are. Not because they're broken, not because of errors, because time itself runs at different speeds. Think about that. You and I agree on what a meter is. We build identical meter sticks. They match, always. But time is fundamentally different in your attic than in your basement. No correct time exists. Only the time each clock experiences in its own location. Gravity doesn't just pull on objects. It warps the very fabric of time and space. If your brain is resisting this, drop a comment right now, because I'm about to prove it. And the proof is so simple, so elegant, that once you see it, you'll never think about gravity the same way again. Imagine a rocket ship, far from any planets, far from any stars, floating in the void of empty space. The ship is enormous, 100 meters from floor to ceiling, and it's accelerating upward, exactly 1 gram, the same acceleration you feel from Earth's gravity standing on the surface. Now do something simple. Put an identical clock at the front of the ship, the head, another identical clock at the back, the tail. Clock A, clock B. Here's the setup. Clock A at the front emits a flash of light. Every second, you're sitting at the back, at clock B, watching those flashes arrive. Question: do the flashes arrive at clock B exactly 1 second apart? According to clock B's ticking, your instinct says yes. The clocks are identical. Clock A flashes every second. You should see flashes every second, but you'd be wrong. Here's why. Clock A emits its first flash. The ship is at position 1 in space. The flash travels down the ship, 100 meters, speed of light. But while that light travels, the ship accelerates. By the time light reaches clock B at the tail, the ship has sped up, moving faster than when the flash was emitted. Now clock A emits its second flash. 1 second later, by clock A's reckoning, the ship is now moving even faster. This second flash travels toward clock B. But here's the key. Because the ship is moving faster now, the distance the light must travel is shorter. The ship is chasing the light. So the second flash doesn't travel as far as the first. It arrives at clock B in less time. What does this mean? Sitting at clock B, you see the 2 flashes arrive less than 1 second apart, even though clock A emitted them exactly 1 second apart by its own ticking. You at clock B experience them closer together. From your perspective at the tail, clock A at the front appears to be running fast, Reverse it. Let clock B emit flashes. Someone at clock A observes them. Same reasoning. The flashes take longer to reach clock A because the ship accelerates away from them. From clock A's perspective, clock B runs slow. Everything is consistent. Back of accelerating rocket, clocks at the front run fast. Front of the rocket, clocks at the back run slow. So far, just special relativity, combined with acceleration. Not too shocking. But now comes the devastating move. What if you can't tell the difference between an accelerating rocket and sitting still in a gravitational field? What if gravity and acceleration are the exact same thing? Hit like if you see where this is going, because this is about to shatter everything. Einstein's principle of equivalence is deceptively simple. If you're inside a closed box with no windows, no experiment exists. None. That can tell you whether you're sitting still in a gravitational field or accelerating through empty space. Let that sink in. Rocket ship, engines firing, accelerating at 1 gram through vacuum. You feel force pushing you into the floor. You drop a ball, falls to the floor. 9.8 meters per second squared. Now imagine, identical rocket ship, sitting on the launch pad, on Earth. Engines off. You feel force pushing you into the floor. Drop a ball, falls to the floor. 9.8 meters per second squared. No way to tell which situation you're in. Gravity and acceleration are equivalent. Not similar. Not analogous. Equivalent. You might say, wait, that can't be right. Gravity is a force caused by mass. Acceleration is just acceleration, totally different. You'd be thinking like Newton. Newton agreed with you. Gravity is a force. Forces cause acceleration. Fundamentally different things. Einstein said no, they're the same thing. And here's why this matters. If gravity and acceleration are truly equivalent, then everything we figured out about clocks in an accelerating rocket ship must also be true for clocks in a gravitational field. Go back. Rocket ship. Clock A at the head, clock B at the tail. We found that when accelerating, clock A runs faster than clock B from the tail's perspective. Now replace accelerating rocket ship with gravitational field. Clock A on a high shelf, clock B on the floor. If equivalence principle is correct, clock A must run faster than clock B, not because of any mechanical difference, but because time itself flows faster at higher positions in a gravitational field. And here's where it gets even stranger. In the rocket ship, you could say clocks just appear to run differently. Doppler effect, relative motion. But in a gravitational field, no motion. Clock A sits still on the shelf. Clock B sits still on the floor. Neither moving relative to the other. And yet clock A is aging faster. This isn't illusion. Not measurement artifact. Time. Actual physical tick-by-tick time. Flows at different rates in different places in a gravitational field. Live your entire life on that high shelf. You age faster than someone on the floor. Your biological processes run faster. Your heartbeat ticks away more seconds. You experience more time. Now the question, how much faster? How big is this effect? Can we calculate it? Yes, and the numbers will shock you. But before the math, let me tell you about two physicists who tested this in 1971. Joseph Haffel and Richard Keating did something crazy. They bought tickets on commercial flights around the world, eastward, then westward, with atomic clocks in their luggage. Airport security thought they were insane. They weren't. They were testing Einstein. The idea was simple. Fly atomic clocks at high altitude. Different gravitational field, different velocity. Both cause time dilation. Bring the clocks back. Compare them to clocks that stayed on the ground. If Einstein was right, the flying clocks would show different times, predictably different, calculably different. They flew. Commercial airlines, regular passengers sitting next to physicists with atomic clocks in carry-on bags. They came back, compared the clocks. The differences matched Einstein's predictions, within experimental error, perfectly. Time had actually flowed differently for the clocks in the airplane than for clocks on the ground. This wasn't theory anymore. This was measurement. But how much different? Let's calculate. If you're still with me, leave a comment, because here comes the beautiful part. The calculation is surprisingly simple. Two clocks. Clock A at height h above clock B. Clock A emits light signals. Ticking. Clock B receives them. If the system accelerates upward with acceleration g, like our rocket ship, then by the time light from clock A reaches clock B, the receiver has gained velocity. Using Doppler formula from special relativity, the frequency received at clock B is higher than frequency emitted at clock A. The ratio is 1 plus acceleration times height divided by speed of light squared. Now the key move, equivalence principle. Replace accelerating upward at g with sitting in gravitational field with acceleration g. Result is the same. Clock A at height h above clock B in gravitational field, g ticks faster by a factor of 1 plus gh over c squared. Plug in numbers for Earth. Gravitational acceleration, 9.8 meters per second squared. Height difference, 1 meter. Your floor to ceiling. Speed of light, 300 million meters per second. The factor, 9.8 times 1 divided by 300 million squared. About 1.09 parts in 10 to the 16th. A clock on your ceiling runs faster than a clock on your floor by 1.09 parts in 10 to the 16th. In real time, about 90 nanoseconds per day, per meter of height. Tiny, utterly imperceptible in daily life, but real. Now scale up. GPS satellites. GPS satellites orbit at 20,000 kilometers above Earth's surface. Gravitational field is weaker up there. Time runs faster. How much faster? Same formula. GPS satellite clocks run about 45 microseconds faster per day than clocks on the ground. 45 microseconds might not sound like much, but light travels 300 meters in 1 microsecond. Without correcting for this time dilation, your GPS position would drift by 13 kilometers per day. Within hours, GPS would be useless. And here's the beautiful part. We do correct for it. GPS satellites have atomic clocks on board. Those clocks are deliberately set to tick slower before launch, to compensate for gravitational time dilation they'll experience in orbit. This isn't theoretical, not speculative. Every time you use GPS, you're relying on Einstein's general relativity, on the understanding that time flows differently in different places. Drop a comment if you've never thought about that using Google Maps. GPS is just one example. Gravitational time dilation has been measured in laboratories, in airplanes, even comparing clocks on different floors of a building. The evidence is overwhelming. Time really does flow differently depending on where you are. The first confirmation came in 1959. Robert Pound and Glenn Rebka at Harvard. They used gamma rays, traveling up and down a tower, 22.5 meters tall. Gamma rays emitted at the bottom were redshifted. Their frequency decreased by the time they reached the top. By exactly the amount predicted, time was running slower at the bottom of the tower. Precision was incredible. They measured a frequency shift of 2 parts in 10 to the 15th, matching Einstein's prediction to within 1%. Since then, increasing precision. In 2010, scientists at NIST used ultra-precise optical atomic clocks to measure gravitational time dilation over a height difference of just 33 centimeters, 1 foot. They could detect the difference in time flow between a clock on a lab table and a clock on a small platform above it. 1 foot, measurable time dilation over 1 foot. But the most dramatic everyday proof is GPS. Global Positioning System, network of satellites orbiting Earth, each carrying atomic clocks, broadcasting timing signals. Your GPS receiver uses those signals, calculates your position by measuring how long signals take to arrive. Absurdly precise. Your position is calculated based on the time light takes to travel from satellites to your receiver. Light travels 30 centimeters in 1 nanosecond. Timing off by a few nanoseconds, position wrong by meters. Gravitational time dilation causes GPS clocks to run 45 microseconds per day, faster than ground clocks. That's 45,000 nanoseconds. Without correction, GPS drifts 13 kilometers per day. But there's more. Satellites are moving 14,000 kilometers per hour, causes time dilation from special relativity. Moving clocks run slower. This effect causes satellite clocks to lose 7 microseconds per day. Net effect, plus 45 microseconds from gravitational time dilation, minus 7 microseconds from velocity time dilation. Total plus 38 microseconds per day. GPS engineers account for this, setting satellite clocks to tick at a slightly different rate before launch. Clocks are pre-adjusted, so once in orbit, experiencing both gravitational and velocity time dilation, they tick at the same rate as ground clocks. This adjustment is baked into the system, not optional. Without it, GPS wouldn't work. Every time you navigate with your phone, you're proving time flows differently in different places. Hit like if that just blew your mind. So we've proven time runs differently at different heights. But what does this mean for you, personally, right now? What does it mean that your head is aging faster than your feet? Let's get personal. You're sitting there watching this video. Your head is 1.5 to 2 meters above your feet, depending on whether you're sitting or standing. We calculated. Time runs faster by 90 nanoseconds per day per meter of height. Over a day, your head experiences 150 to 180 nanoseconds more time than your feet. Over a year, 55 to 65 microseconds. Over a 70-year human lifespan, your head ages about 4 milliseconds more than your feet. 4 milliseconds doesn't sound like much. It's not. You'll never notice. But it's real. Your brain has experienced more time, more tick-tocks of the cosmic clock than your toes. Think bigger. Spend your whole life at high altitude. Denver, Colorado, 1,600 meters above sea level. You age slightly faster than someone at sea level. Over a lifetime, difference is 100 microseconds, a tenth of a millisecond. Still tiny, still imperceptible, but real. Now go extreme. Stand on the surface of a neutron star, which you can't because you'd be crushed into a pancake. Time would run about 30% slower than in deep space, far from any gravitational field. Every second you experience, someone far away experiences 1.4 seconds. Near the event horizon of a black hole, time dilation becomes infinite. Time effectively stops. Imagine this. Your twin falls into a black hole. You watch from a safe distance. From your perspective, they slow down as they approach the event horizon, moving slower and slower and slower. They never cross. They appear frozen at the edge. Forever, light from them becomes increasingly redshifted, eventually invisible, but they never fall through. From their perspective, completely different. They fall through the event horizon in seconds. Nothing special happens there. They keep falling toward the center. Both perspectives are true, both real. Time is local. Time is what your clock measures in your location. This is what gravity really does. It warps space-time. Not just that objects fall, the very fabric of time is stretched and compressed by mass. And here's the thing that should disturb you most. No absolute time exists. No universal clock ticking the same seconds everywhere in the universe. Time is local. Time is what your clock measures. Your clock measures something different than my clock if we're at different heights in a gravitational field. Profound implications for causality, for the nature of reality, for what we mean when we say now. Look up at the stars. You're not seeing them as they are now, seeing them as they were when light left them. But even that phrasing is misleading, because now doesn't have universal meaning. Your now on Earth is different from the now on a GPS satellite, different from the now in a distant galaxy. Once you accept time is relative, that it flows differently in different places, you must let go of the idea of a universal absolute timeline. Time is not a river flowing the same everywhere. Time is a landscape with hills and valleys where the flow changes depending on where you are. Remember at the beginning, your head ages faster than your feet. Now you know why. Gravity isn't pulling on your body. Gravity is bending time itself, making it flow faster the further you get from Earth's center. Your head is slightly further from Earth's center than your feet, experiences slightly weaker gravity. Time flows slightly faster there. Not that your head is moving through time faster. Time itself is moving faster at your head. That's gravitational time dilation. That's what we've uncovered. And that blows apart everything you thought you knew about time. Now a question for you. If time flows differently in different places, does that mean the future isn't fixed? Does it mean simultaneity? The idea of two events happening at the same time is meaningless? Drop your thoughts in the comments. Let's debate this. And if this made you see time differently, hit subscribe, because we're just getting started. Next up, why you can never actually see the color of an object. What you call red is nothing but a lie your brain tells you. You won't believe what color actually is. Thanks for watching, and remember, your head is aging faster than your feet, right now, every second. That's physics, that's reality, that's beautiful. See you in the next one.